We are now on to dynamic routing protocols. So we have escaped the drudgeries of configuring static routes now, and we're going to rely on our dynamic routing protocols to help us out. So from here on, we're going to be talking about dynamic routing protocols, the basic information on them, and we'll go into configuring some of them and go from there. So dynamic routing protocols have been around for many decades. Some of them that are even used today date back to the 80s even. One of the oldest is RIP. So that's the Routing Information Protocol, RIP. And there are two versions. There's version 1 and there's a version 2. And RIP version 1 is classful, and RIP version 2 is classless. So the classful was really only useful back in the day. Remember I mentioned when we were basing the subnet mask on the class of the IP, so that first octet, based on whatever octet you had IP in that first octet there, you would get a certain subnet mask by default. So that was that classful scheme. So RIP v1 helped us dynamically share those routes in that sort of situation. Once we moved to variable length subnet masks with classful subnetting, or classless subnetting, and classless interdomain routing, CEDR, we needed something a bit fancier, so RIP was updated, and we now have RIP version 2. Unfortunately, RIP is not a very fancy protocol. It's relatively stupid from the basic method that it works. So Cisco has decided to not teach RIP anymore. Most people have decided to move on to other things like egrep and Ospf. So that has been deprecated from our curriculum. RIP was actually taught up to the last revision, but no longer. But we'll talk a little bit about how it works on when it boots up and does its route sharing. But beyond that, we're not going to go into RIP configuring. Although once we get into doing some egrep and Ospf, I'll probably mention it because all the dynamic routing protocols honestly are configured very similarly. So RIP is very much the same as the others. So we'll get to that. So there have been other protocols that have been developed since then. So a couple of those are Open Shortest Path First, OSPF. That's an open standard. That's why it says open in the beginning. And that's been around for quite a while as well. They've got a very fancy back end to it where all of the different routers know of all the other links in the entire network, and they build an entire topology internally, and then it determines what the shortest path in order to get to a certain network. So that's a very interesting protocol, one of my favorites. We also have intermediate system to intermediate system, so IS. That's something we do not go into in depth in CCNA. It's been around for quite a while as well, and is something that used to be taught in CCNP, so that's something you can learn about as well. It's used in some larger organizations. We have IGRP, Interior Gateway Routing Protocol. And this was an older Cisco proprietary protocol. It's been deprecated in favor of the new version of it called EIGRP, or as I say, egrep. So EIGRP. So it's the Enhanced Interior Gateway Routing Protocol. We will be configuring OSPF and egrep going forward here. Egrep is a distance vector routing protocol, which we'll go into, and OSPF is a link state routing protocol. Originally, egrep was touted as a hybrid routing protocol because it kind of does similar things where it bases off of hops, so it's a distance vector, but it also does some link state type functionality. So some of the older documents you may see will refer to egrep as a hybrid routing protocol, but they have since dropped that and now refer to it solely as a distance vector routing protocol. These are all interior routing protocols. There's one exterior routing protocol, BGP, Border Gateway Protocol, that we will not go into in CCNA. That's a CCNP thing. So if you wish to learn about that, you'll have to further your studies. That is for traveling from organization to organization when you're talking about the internet. Large groups of networks on the internet are called autonomous systems, and BGP lets you communicate between those autonomous systems. And then within an autonomous system are these. So we're going to focus on inside your own network, inside your autonomous system. If you want to get into routing between them, now you're talking BGP, and that'll be for CCNP studies. So routing protocols, they provide simplicity for us as IT professionals. They allow for discovery of new networks. The automatic route updating. Best path determination. Failover. Remember I was mentioning on the last video, failover is kind of a nuisance when you're talking static routes, and also for load balancing, which is usually goes hand in hand. And ease of administration. So when with all this happening behind the scenes, we don't have to go into those 6 different routers and add a dozen routes on every single router in order to make traffic work correctly. It simplifies our life, and it also gets rid of typos. So, gets rid of human error and typos. So that's not as much of an issue. As long as you configure your routing protocol correctly, things should work relatively well. So the interesting way routing protocols work, they work different. Each one works differently, but they're in 2 categories. So we're going to talk about RIP right now, even though we don't teach it from a configuration standpoint. The basic idea is all of these I'm going to circle are distance vector protocols. And we have a link state protocol here. The distance vector protocols, they base themselves off of hops, and the very basic ones like RIP, they will simply share their routing table from one router to another. So the way RIP basically works is when a router comes up and it boots up, it will take a look at its connected network. So if you look in its route table, it's going to say, look at all my connected stuff. I've got 10 dot something and 192 dot something, and all these interesting routes that I'm directly connected to. It will then send that out to another router, and it'll say, hey, check this out. Add this into your routing table if you don't have it. So this router might have 10 dot 192, but it doesn't have that 17, but it has the other ones. So it'll then say, oh cool, thank you, so I'm going to add this in here, and by the way, yeah, here's all my routes too, you should add that in if you don't have it. So then they'll go back and forth and they'll share their routing tables, and every so many seconds, like every 30 seconds or so depending on your configuration, these routers will share their entire routing table back and forth, so that everyone is synchronized. So the problem though is with convergence. So with this kind of design, if you have a whole bunch of routers in a line, for example, this could be a big grid of routers, but if you have a bunch of buildings interconnected or something like that, we have router. This could take quite a while for it to propagate from one to the other, because we're going to have that delay potentially from one router to another. So when something changes, like this link goes down, for example, it could take a very long time for that to replicate throughout your network. Meanwhile, someone over here is trying to get there, and they can't get there because they'll get partway there, and then their traffic will fail. So that's some of the cons to using some of the older protocols like RIP. And for link state protocols, they work on more of the idea that have this whole topology, and everyone has a table of links. And let me draw this out here. We'll clear this. If we have a router and another router, and they have a bunch of links, and then those two are interconnected through some way. Each one of these, whenever I make this little T, that means it's like a local network of some kind. It's a bus-based network, like a Ethernet network, for example. Each one of these routers will share this link information to the other connected routers. So the idea being that instead of saying, here's my routing table with all my connected routes, it's going to say, here's some link information. Oh, here's another packet with some other link information. Here's some other link information. Here's some other link information. And we'll get into the more of the details on OSPF, but and then in return the other one will do that too. And then everyone will build a table and a topology essentially of, here's all the different links that I know about. Are they up? Are they down? What's the network that's off of that link? Etc. And then it will build a routing table off of that topology that it learns. So it'll learn all of the different links that are out there. Instead of just saying, with RIP, for example, it will eventually learn how far away a network is based on how many routers it has to traverse. These link updates also are much faster. So instead of being sent on a periodic timer, these link updates occur immediately. So if a link comes up, we plug something in, it'll immediately say, hey, check this out, I got a new route. There's a new link over here. If a link goes down, it'll say, hey, careful, watch out, this died. And then they'll quick share all that information around. That's kind of why I like OSPF in that manner, because it's inherently faster by design, and it's got this interesting feature where they build their topology table behind the scenes. And egrep has some of this link sharing capabilities that we'll go into, where it'll do a triggered update, but it's still behind the scenes, does a similar manner to RIP. And I just realized I misclassified ISIS. That's actually a link state as well. That's my fault. So with this link state, OSPF and ISIS, they have a faster convergence time. So a pro would be convergence time. Due to this fast updates with the link information, you don't have to wait 30 seconds or 15 seconds or something like that every single hop in order to get that data sent to you. It's immediate, so it'll immediately say, here's a link. Oh yeah, tell my neighbors, tell my neighbors, tell my neighbors, and it'll go down the line. From here, we're going to go into configuring some protocols and discussing distance vector a little bit more. I kind of glossed over it a little bit, and we'll get into that. And I may throw in configuring RIP as well, just because it's such a simple protocol. So look forward to that.